position and velocity and so forth, acceleration. If I put it, see what's to your right would be to my left. We call this plus. And I let it go and it swings. It goes from plus to minus, plus to minus, plus to minus. Now, if this is plus, then which way is it being pulled?
To minus.
To minus. See, this is the minus side. And when is the pull the maximum? See, there's no pull there. The pull is the maximum when it's here, but it's minus. And it's a maximum here, but it's plus. But where's the position of maximum? There, but it's plus. And where's the velocity of maximum? At the bottom. See, it's not going, it stops here and then it's going to maximum here. I can lay all that out on this diagram in terms of phase. If this is the position, which I call L for length because I measure it in terms of inches length, then in terms of the cycle. This is the beginning of the cycle. This is halfway through the cycle. This is quarter way through the cycle. And of course, on the way back, this is 3/4 of the way. So the position is a maximum here, that's we'll call plus. The velocity is a maximum here, which is halfway through, or a quarter way through the cycle. And if I could think of it going back and forth or just going around, the point is it gets back to this point at the end of the cycle. So here's V plus, and here's L minus, and here's V minus. But we recall that the acceleration was negative over here, so I'll put A minus. And the acceleration was plus here, so I'll put A plus. So I could leave out the minuses and just say position maximum here, acceleration maximum at this cycle, with a velocity maximum here. So I want another term for this negative velocity. Now you wouldn't get that until I do some little more playing with it. I could let you do this yourself. You could feel it. How do I stop it? In fact, how do I make it go? If I go against the swing, I make it go faster. If I go with it, I stop it. So it enables me to say that the control is opposite the velocity. And these four are another example of the fourness. I've tried to do it just in visual terms, but the mathematical expressions would be the calculus. This is known, well, this is length, and velocity is the first derivative of length. Velocity, this is what Newton did. He said, let velocity equal, there wasn't any term like velocity. He said, but that thing we call motion, let it be length divided by time, which is what we say it goes 10 miles an hour or 50 miles an hour, or 10 feet a second. So much distance, L, per unit of time. Well, then if I said my Volkswagen can get to 60 miles an hour in 10 seconds, that would be acceleration. But notice that I say miles per hour per second. I've got time in twice. And to make that very simple, I say L over T squared. Each time I divide by time, I put in another T there. And this one is control. It's the rate of change of acceleration. See, acceleration was the rate of change of velocity. I can go to 60 miles an hour in 10 seconds. That would be different from going to 60 miles an hour in 1 second. Or if I hit a telegraph pole, I'd go to 0 miles an hour in a very small fraction of a second. That would be unbearable. So the control, the change of acceleration, when I push the accelerator or put on the brakes or even steer it, they're control. Now Newton only went this far. And I don't know whether he explored that or not, but what was picked up was with acceleration, position, and velocity, you can work all this clockwork out and figure everything. And that's all there is to it. There isn't any free will. But I say that's taking it one more step. The control function provides